Welcome back, everyone. So the first speaker of this afternoon is Ian Vonk, who will give the first lecture of his series, Rational Points on Modular Curves. So,
all right. Thank you very much. Can everyone hear me all right? Yeah, okay, great. So thanks for the introduction. And first of all, thanks very much to the organizers for having me. It's really a tremendous pleasure and an honor to be able to speak here. So thanks very much for putting together this wonderful program as well. So I would like to begin my course, but before that, a couple of maybe practical announcements. The first is that in principle, you shouldn't have to take any notes because I started typing up notes, and as usually happens in these types of scenarios, I get too enthusiastic and I get carried away and the notes become way too long. So as a consequence, yeah, they're about 50 pages long now. I've posted them on my own website because please don't read beyond the first chapter for now. Everything else that comes later is still a little bit unpolished, but as we go through this week, I'll be updating these notes as we go along so that they'll be hopefully perfectly finished by the time you'll actually need them. So you can find them on my webpage. The URL is on the board. If you can't find it, let me know, and then I'll give you the more specific URL, but that one's a little bit long to write on the board, so I gave you the shorthand version. All right, so this course is about rational points on modular curves, and we already learned this morning in Pierre's address that on the one side of this meeting, of this workshop, we'll have a lot of attention for the method of Chaboty and some non-abelian analogues of it, which is a very general method. So it applies to curves with some geometric properties. But modular curves are, of course, a singular example, not singular in the geometric sense, just they're very special curves. So they have lots of really fine-tuned arithmetic encoded in them. And so that's really what the focus of this lecture course will be about. It's also less about Chaboty, in fact, almost not at all. And I'll focus really on the geometry of modular curves and their rational points. And so specifically, the goal of this course is to systematically construct rational points on modular curves maybe those modular curves will be denoted by X, and they'll be defined over some number field. And we'll also look at the consequences for the Mordell-Weil groups of elliptic curves. So specifically, we'll look at elliptic curves defined over Q, but more generally, abelian varieties that are known to be modular. And this will come through the study of the modular parameterization, which we saw this morning in Professor Gatte's talk. It's known that every elliptic curve can be uniformized by a modular curve X naught of n. And so specifically, if we manage to construct lots of rational points here, they may give rise to interesting sources of rational points on elliptic curves as well. So more concretely, there's two sources really, and this is the only two sources that we have of systematic point constructions on modular curves. They have very different flavors. So two principal sources. The first will be a systematic study of cusps. Yeah, cusps give rise to systematic rational points on modular curves. And so in this context, we will study also the arithmetic consequences for the Mordell-Weil group of elliptic curves, specifically for the torsion part, coming in the work of Mesa, which will be discussed next lecture and the lecture after. The second very important source of rational points comes from the theory of complex multiplication. The theory of complex multiplication, as we'll present it, I won't give many proofs, unfortunately, because there isn't much time, but the notes contain much more background on that as well. The theory of complex multiplication gives rise to a systematic family of points on X naught of n, which we can trace through to the elliptic curve E. And we can then study when these points give us non-trivial points, potentially maybe of infinite order. This will be discussed in the final lecture, as we will talk about the work of Gros and Zagier and Kolyvagin. Okay, So today I'd like to begin with a bit of motivation. So we want to set the stage and we want to explore this picture a little bit further and to see what these groups look like and why constructing points on modular curves might be very interesting. And I'll start very accessibly, I think, with a more historical discussion of the Mordell-Weil theorem. So Mordell-Weil groups. And I'd like to begin with the first known occurrence in the research literature of an elliptic curve, at least to my knowledge, but that doesn't mean much, which is in the work of Diophantus. Diophantus in his Arithmetica, book 4 to be precise, gives us the following problem. So I'm not going to write it down because it's just motivation. Take a number n. You got one? Okay. Now split the number into two parts. Yeah? So the two numbers that you get out must add up to n. But instead of adding them up, you're going to multiply them together. Now, can you do this in such a way that the result is a cube minus its side? That's what Diophantus asks. So in algebraic terms, Diophantus asks us to solve the following problem. So Diophantus asks for a rational solution. Really, that's what we should that's how we should interpret this question. So for a rational solution to the curve, we took our number n, and then we split it into two parts that have some n. So I can say y and n minus y are these parts, and we multiply them together, and this must be of the form x cubed minus x. Yeah? That's what Diophantus asks us to solve. Now, if you look at this problem, it doesn't seem very difficult. Yeah? I can find tons of solutions on this one. 0, 0 is a solution. But of course, Diophantus, he wasn't really such a big fan of this concept 0 or negative numbers. These things weren't really around in his day. So he was really looking for positive rational solutions to these, whereby everything in sight must be positive. X must be positive, y must be positive, and n minus y must also be positive. And then suddenly, it's not so easy anymore to spot any simple solutions. And here's what Diophantus does. And if you picked 6 in your head, then you pick the same number as Diophantus. So Diophantus solves this in his book for n equals 6. And he does it as follows. First, he does a mysterious thing. He says, suppose that x is equal to 3y minus 1. Okay, let's suppose that. We don't know where that comes from at this stage, but we can see why it's useful, because then substituting this back into this equation, we get a cubic equation for y, which is actually a very easy cubic equation to solve. So then substitution gives us the equation 27y cubed minus 26y squared equals 0. And now this one I can solve. So it's got a double root y equal to 0, and then it's got this other root, which is, I guess, 26 over 27. You know? So Diophantus constructs a solution, which comes down to 17 over 9 if you work out the x-coordinate as well, and then 26 over 27. There we go. Now, what does that mean, and where does this assumption come from? Well, what Diophantus was doing here is really geometrically, we can interpret this. If we plot the elliptic curve for 1 second, it looks a little bit like this. So for n is equal to 6, it has the following shape, something roughly like this. Okay. Now, what is this line? What is this equation that Diophantus used here? This line really is the tangent line to a very easy but illegal solution. Minus 1 comma 0. It's illegal because it contains 0 and negative numbers. And now we're going to construct the tangent line to this elliptic curve. And that's precisely the equation that's given here. So geometrically, that's what he was doing, really. He was computing the tangent line because the third point of intersection now is very easy to compute because we already have a double root there. And so it's quite fascinating that already Diophantus, the first time anyone, to my knowledge, ever wrote down an elliptic curve, he already implicitly made use of the group law that we saw this morning in Professor Gatti's lecture. And so this is what we might call the method of ascent. Yeah. So you start from a simple solution and you produce more solutions by adding points on the elliptic curve. So the question is, can we reverse this process? And this is really what Fermat did in the 17th century. So he reversed this process and he came up with the method of descent, which of course we all know nowadays, but I'd just like to point out that this occurs in his work on the Fermat equation of the exponent 4. So he reverses the procedure, which what we might call descent. And what he does is he really uses a pair of dual isogenies and the pair that's relevant is, well, the first one, which is the one that he started off with thinking about. So that's x to the 4 minus y to the 4 equals z squared. He showed actually that that does not have any non-trivial solutions, the trivial solution being one where one of the coordinates is 0. Yeah. That implies Fermat's last theorem for exponent 4. It's a bit stronger. And what he does is, it's very interesting. He considers in his descent argument, really implicitly, you have to unpack it a little bit, a second elliptic curve, which has a different equation. It's u to the 4 plus 4 times v to the 4 equals w squared. Yeah? So we might call the first one E1 and the second one E2. Of course, to make them into elliptic curves, I secretly chose an origin, which I didn't tell you about. But you can find more of these details in the notes. Yeah, 1, 0, 1, I think is what I chose for the origin. Okay, now these maps here also have explicit shapes. If you look in his work, so we have what I'll call a phi 1 and a phi 2. And if you look at the argument, the conclusion really, the argument is in the notes, is if you unravel it, literally a descent by 2 isogeny. So his argument, it shows two things. It shows that when you take E2, the rational points on it, and you quotient out by the image of the rational points of E1, then that's a cyclic group of order 2. So in fact, he does it both ways, and I'll write down both of these equalities here. So phi 2 E2, yeah, Q. This quotient is Z modulo 2Z, and also the other way around, he shows that E2 Q modulo phi 1 of E1 of Q is also isomorphic to Z modulo 2Z with explicit generators. So you can find the details in the notes. And of course, he doesn't use the language of elliptic curves at all. Yeah, that's just our projection. That's just our interpretation of his argument. Okay. All right. So it follows from this what the Mordell-Weil groups are of these. I'm not going to spell them out. They're both rank 0. Yeah? One of them has a torsion of order 4, and then one of them is cyclic, namely E1 has a cyclic group of order 4 in its torsion, and the other one is a Klein 4 group. Now, all of this, these constructions, and the construction also of Diophantus, this was formalized, really. This method of ascent, of adding points on elliptic curves by Poincaré. So after Diophantus, it took a tremendously long time before this was formalized by Poincaré. He defined the group laws on Jacobians of curves. That's what he did. And he asked in his paper, if we reverse this process on general elliptic curves of adding points to itself or to other points and producing more points from old ones, what's the minimum number of solutions that we must start off with to be able to produce any solution at all? Yeah? And he calls this the rank. That's why we still call it the rank nowadays. So how many generators are needed for this group, which he formalized of the Jacobian of a curve rational points? And he sort of implicitly assumes it's finite, or he sort of hints at it that it's finite. But of course, we learned this a little bit later in the celebrated theorem of Mordell-Weil. First, for elliptic curves over Q by Mordell in 1922, and then for abelian varieties by Weil where the key step in Wei's argument was to generalize the notion of what happened in Fermat's descent procedure, which is the basis for Mordell's proof, into a notion of producing a smaller solution. Yeah? So that's what happens in the method of descent. You start with a fictional non-trivial solution and you construct a smaller one, where smaller means the absolute value of the coordinates is smaller. And so that notion of the absolute value of the coordinates being smaller is what was formalized by Heitz, by Wei. Okay. All right, now, so the theorem is the following. Suppose I have an abelian variety over a number field. So K is a number field. Then its Mordell-Weil group is finitely generated. So the set of rational points viewed as a group with this group structure that Poincaré defined is finitely generated. There's always a finite torsion part. And then we have a free part where the power is called the rank after Poincaré's terminology. Okay, now in the proof of this, I already mentioned there's really two steps. And the first step is really the key point in the argument. We'll hear a lot about Heitz in the other lecture courses, so I'll skip over that part and talk about the weak Mordell-Weil theorem instead. So the key step is the statement that the so-called weak Mordell-Weil group, so AK modulo NAK for some positive integer n, well, I guess bigger than 1, is finite, which is certainly implied by this theorem, but the converse is also true by this Heitz argument that I'm not mentioning. It's finite. And this should be true for some n. Okay. Now, what you could do is, if you picked such an n, you get a short exact sequence of this abelian variety. When I write A, you can just think of it, if you will, as the geometric points over K bar. And I have a multiplication by n map, which is going to be a surjection. And the kernel of it is what I'll call AN, and I'll try and use this notation throughout this lecture course. So from this short exact sequence, which is really the defining short exact sequence for this kernel, AN, we get a commutative diagram in Galois cohomology, where I get an injection from my set of rational points modulo NAK. So that's the co-kernel of this map. So 0, 2, and now I'm going to cohomology classes for the absolute Galois group of K, valued in whatever the kernel was there, so that's AN. And I go to the next term up, KA, and I know that I'm going to be n torsion because I'm in the kernel of the next map, and in fact, that is a surjection. So we get a commutative diagram like that, except there isn't really anything to commute yet. Because whether we work with K or with some completion, it gives us the exact same diagram. And so what we could do is we could form the same diagrams over all of the completions. And we get natural maps like this. And I can now do this for all the completions that I get. So V will run over all of the places. So I'll just write V and I'll say it in words. It runs over all of the places of the number field K. Infinitely many factors in this product. Okay. And then finally, this one. And I get maps going across like this, and that's what the commutative is. It's a commutative diagram. Oops. Essentially just by definition. Okay, I'm told not to cross this line, so I'm going to go all the way back to the left. So what I'm gearing up to do really is familiar territory for all of you. It's proof of the weak Mordell-Weil theorem, but I'd still like to do it, even though you've seen it probably in Silverman's book for the case of elliptic curves, because I'd like to single out a couple of the ideas. And I'd like to reformulate it in a more algebro-geometric language that doesn't use Galois cohomology, but is more geometric, because it'll prepare us for some of the arguments of Maser to come. So that's what I'm trying to do here, is I'm going to reinterpret this argument. Okay, so first of all, definitions. So we define in this diagram the Selmer group and the Tate-Shafarevich group to be the kernels cell n a over k, if I want to be really explicit about it, is defined to be, well, now I'm going to take the kernel, I'm going to take all of the elements in this Galois cohomology group, h1k, an, that map in the product over all the places kv, a to 0. And I'll make a similar definition where now instead I take those classes at the end. Like so, and I'll call that the Tate-Shafarevich group. Okay. Oh, H1, sorry, thank you. Okay. These are two tremendously important groups associated to an abelian variety over a number field. And so if you look at the diagram here, we see that in fact, the image of the global points, or the global weak Mordell-Weil group, which is this group here, it lands inside the H1K AN. And so if I follow through this map here along the diagonal, that's essentially the map whose kernel we've taken to define the Selmer group. And because this diagram is commutative, we see that we can also go down the bottom. And so we must end up at 0 in the target. So in other words, we can refine this really, and we can be more specific about the image of the weak Mordell-Weil group. It lies inside of the Selmer group. In fact, we obtain an exact sequence which will take us from the weak Mordell-Weil group, so AK modulo NAK, into the Selmer group. And the co-kernel of that, if you unpack it, is exactly the Tate-Shafarevich group, or at least the n torsion of the Tate-Shafarevich group. Okay. Now, the amazing thing about this, and this is really the only proof of the Mordell-Weil theorem that we know, is that this group is finite. The Selmer group is finite. As a consequence, this group, which is a quotient of it, is also finite. So the n torsion in the Tate-Shafarevich group is finite, and we conjecture that in fact this whole group is finite. We can't prove it, unfortunately. Okay. Now, how does this theorem go? Right, so I called it a theorem, which I think is justified. I'm not going to change it. Now, here's how we're going to prove this. So first of all, we're going to choose a set S, the set of places finite places, which consists of all of the places of bad reduction of this abelian variety, as well as all of the places that divide n, where n is this number that I've chosen to do my descent with respect to. So those places I'm going to stay away from. They're very bad. And so later on, we'll see that we might want to be a little bit less lazy than this. But for now, it's fine. We just want to prove finiteness. Okay, so A, you see, this abelian variety A has good reduction outside of the primes in S. Yeah? So I can find some abelian variety and now I'm going to spread out over the base U, which is the spectrum of OK, the ring of integers in K, where I invert all of these primes that I want to stay away from. So these are my choices. That's the situation we're in now. And what we're going to do now is to observe that, well, you see, this Selmer group, how we defined it, is always going to be unramified at all of the finite places outside of S. Yeah? And another way of saying that is that it's actually contained in the étale cohomology group of U, where I take the n torsion on this abelian scheme over U. Because that thing, well, that's contained inside of H1, the Galois cohomology, KAN, and in fact, it consists precisely of those classes that are unramified outside of this set S. Whereas the Selmer group has additional conditions at these bad primes, we're just forgetting them. And we're going to show that if we blow it up to this bigger group, that's still a finite group. All right, now, in fact, it suffices to prove finiteness after allowing ourselves to do two types of operations. The first is I allow myself to enlarge the set S if I need to another finite set that contains it, if necessary. And I also allow myself to prove this finiteness, where instead of proving it over U, I allow myself a finite étale-based change. So passing through some finite étale cover V over U. Yeah? The first one is kind of clear. The justification for the second one is in the notes. Bit of a technical thing. If you like, it follows from the Hochschild-Serre spectral sequence. But you can just take it on faith also. You've seen it in action already if you read the proof in Silverman. Just the language was very different. Now, why is this helpful? Because you see, if I allow myself these two pieces of flexibility, I can now choose my V very wisely. Yeah, so I can choose my V to be spec of OL, where L is some finite extension of K, where I stay away also from all of the primes above S. And I can do it in such a way, now that I know that, that trivializes the n torsion on this abelian variety. If it has some action by the Galois group, I just pass to this finite extension that trivializes this action completely. And so such that this n torsion, which is the classes that we're dealing with here, the coefficients, just become trivial. So at least we know what we're talking about, and we know exactly what the structure of this thing is. So an should be trivial, meaning that it's going to be isomorphic to a number of copies of the constant group scheme, where G is the number of copies required being the dimension of this abelian variety. Yeah? Okay, so that's the first thing I want to demand. And the second thing that I want to demand, because why not? I'm passing to a field extension anyways, I might as well make sure that this Mn is contained in this finite extension. So so the nth roots of unity live on this scheme V. That's what I want to assume as well. Why not? Yeah, I said V, I mean OV, but I hope this kind of thing doesn't confuse too much. Okay, now once we've done that, showing that the étale cohomology group with values in AN now just becomes showing that the étale cohomology with this finite group scheme Z over NZ is actually finite. Yeah? So we have the Kumar exact sequence. Defining the nth roots of unity is a kernel of the map from the multiplicative group to itself, which is raising to the nth power. Now, this is a surjection on V in the étale topology. And that's because n is invertible on the base. Yeah? I've assumed that all of these primes are inverted. This is important. So later on, we'll try and fine tune this for places where it's not invertible on the base. But in any case, this Kumar exact sequence gives us, by passing to the long exact sequence on cohomology, the units in OV. So that's the term coming from the H0, modulo nth powers. This will map to, well, H1 étale of this V with coefficients in Z mod NZ, which is the same as mu n, V. And that maps in turn to the H1 of V of GM, that's the Picard group, and I take the n torsion. It's the Picard group of V. And that surjects also. Now, what's nice about this is, you see, I've written everything in the language of schemes, but the functions from V star, that's just this ring here, that's the units, the unit group in OL 1 over S. The unit group in a number field, and you can invert some primes if you like, is always finitely generated, and therefore this quotient here is finite. That's Dirichlet's unit theorem. On the other hand, here, the Picard group of V, that's just my fancy algebra geometric interpretation of the class group of that numbering, which is also finite, because class groups of numberings are finite. So we see that this mysterious group is flanked by two groups that are not mysterious at all. They're finite. We've already proven their finiteness. It's the two main theorems of classical algebraic number theory. And so that implies that this one also must be finite as required. Okay. So even if some of these words didn't fully make sense to you, try and look at this argument and try and see if you recognize the argument that you know for elliptic curves, because it's really exactly the same argument, just coded in a language that'll give us a little bit more flexibility on this. And in fact, we'll return to many steps in this proof later on when we discuss the work of Mesa. So one important remark, I guess, to make already now is that you see in practice, we often do a descent in practice as well, let's say on elliptic curves. We do this kind of thing all the time. You know, we stay away from some kind of set of primes, S, we pass maybe to some finitesimal cover to trivialize the n torsion points. If we were lucky, this wasn't necessary, right? Because our elliptic curve maybe had all of its 2 torsion over Q, then we don't have to do this second step. Also, if it has lots of primes of bad reduction, it's more work. We know this kind of thing from practice, and so it's worth pointing out that in practice, if we actually want to turn this into an algorithm for computing the rank, we want to find a good bound on this weak Mordell-Weil group by finding a Selmer group that is as small as possible that contains it. And so in particular, we want to take this set S as small as possible. So this means we want S to be small. So maybe it was a bit wasteful to enlarge the set S to make sure, you know, that it had all of these places. Maybe we want to penetrate as much as possible into these bad places in this kind of argument, if we can. You know? That's very much what Mesa is doing in his proof. Because we know that there's a second step. And if we didn't do a good job on this first step, then there'll be a lot of pain and suffering in the second step. Because if the bound is not good enough, meaning that in practice, we'll have maybe some description of what our abelian variety is. For instance, it could be an elliptic curve over Q, and we have some equation for it. we will already be able to produce many classes in this group. We'll find points explicitly by looking at the equation. And so we'll have a kind of a lower bound for this. And if it's equal to the upper bound that we get from the Selmer group, then we're done. We're golden. We don't have to do any work. If the bound is not sharp, however, then we need to investigate. Then the work starts, right? Because then we take all of these classes in the Selmer group explicitly. We write down equations for the twists that they correspond to, and then we check the local solubility of all of these guys at the bad places that we excluded. And hopefully we can rule out all of the classes. And if that succeeds, we will have performed our explicit descent completely. So these steps I won't say anything about, because we will see that for modular curves, we would like to avoid it if possible. We would like to still get this conclusion of determining the rank, determine the rank of AK. At least often, let's say often, but in practice, this has a pretty good chance of working, certainly for elliptic curves over Q. All right, so this is the step here that's bad. Yeah. Because if we do this, we're forced to write down some sort of explicit formulae or forms or things that need to vanish, which for modular curves, that's sort of rule number one when you learn about modular curves: never write down an equation for a modular curve. It should be avoided, certainly for the Jacobian of a modular curve, right? And that's certainly something we want to stay away from. So we see no realistic possibility of doing this second step in a descent. If you go back to Silverman and you look at this kind of step, that's not something you would want to do for an abelian variety or a Jacobian of a modular curve. So we want to avoid it at all costs and make this first step really good. This is sort of the goal. We want to refine our Selmer group sufficiently so that hopefully the upper bound is equal to the lower bound and we never have to get to this second step. And that's what we'll see in action in the work of Mason. All right, are there any questions about this, this first part? We're not really going to use much of it. I mean, the descent formalism will come back later, but it's really all just for motivation. Okay. Now, we have the Mordell-Weil theorem after this step with heights, which I skipped. And so we know that any abelian variety has a finite torsion group, which often we can say a little bit about. So for elliptic curves over Q, often we can usually determine what the torsion is. Determining what the rank is much harder. So knowing something about the rank is a bit of a mystery, and conjecturally, the analytic L function of the abelian variety knows a lot about the rank through the Birch-Swinnerton diagram. So conjecturally, the ranks of abelian varieties are encoded in their L functions. Yeah, so the L function, the definition is in the notes if you haven't seen it before. For elliptic curves that are modular, it's the easiest, even though the general definition is in the notes. It's the L function that you get by forming the Dirichlet series using the ANs that were defined this morning, sequence of ANs that were defined. Again, all of this is in the notes. Now, define a completed L function, which is the same as the analytic L function that we define in the usual way, up to some explicit factors. Yeah? And these explicit factors, they don't really matter all that much. There's a conductor, which is GS divided by 2, which is the norm of the conductor of A defined over the number field K. There is some other term, which is a power of the discriminant of the base field. The power I forget, but it's GS. And then finally, there is a gamma factor divided by 2 pi raised to the power, this one is raised to the power S, and then there's a G times the degree of this field extension. Now those fudge factors, I'm telling you about them because you'll see them come out in a second when I talk about modular abelian varieties, where much more is known about this problem. So we define this completed L function. which converges whenever the real part of this variable s is strictly greater than 3/2. Now this we get from the Hasse-Weil bound, so that's not a deep fact. But what is deep is what I'm about to tell you. Well, what is deep, I can say that, but it's unknown. So we don't know in general the statements that I'm about to make. So it is expected that this L function admits an analytic continuation to all complex values of S. So I said there, it a priori converges when you write it down for the real part greater than 3/2, but we conjecture that in fact it has an analytic continuation to C. And it satisfies a functional equation which is more cleanly stated on the completed L function, which is more or less the same as the non-completed one up to these factors that I've told you about. And so it happens when I take this L function and I shift the argument from S to 2 minus S, and we conjecture that this should be the same as the original L function up to some sign which is plus or minus. Okay. All right, the second statement is that we expect that if we take this L function and we look at this L function, which is now, by our first conjecture, defined for any complex value S in C that I like, I can take in particular the value at S is equal to 1. This may or may not be 0, but if we take the leading term and its Taylor expansion, then it should vanish exactly as many times as R, the rank of this abelian variety. In fact, let me write it out as such. It's the rank of AK. In fact, Birch and Swinnerton and Dyer conjecture more than that. They also have a conjectural expression for the term, the leading term in this Taylor expansion. And all of these quantities, again, are defined in the notes. And since we won't really need them, I'm not going to recall them here for this general abelian variety, as I'm stating. So there is a real period of this abelian variety, which for the case of elliptic curves, is really just the integral over the connected component of the identity of the real points. There are the Tamagawa numbers, which measure the size of the group that you get when you take the neuron model and you quotient out by its identity component in the special fiber. So that's a finite group with some size, which is called CV. Then there is a regulator. And the regulator is defined in terms of the height pairing on the abelian variety. And I didn't give myself enough space, unfortunately, so I'll expand a little bit, which just goes to show how much information is encoded in the L function, at least conjecturally, if we believe Birch and Swinnerton and Dyer. So we have the regulator here, and then we have the order of this mysterious Shafarevich-Tate group. So in order to even make sense of this statement, we better assume that Sha is finite. Yes? Sorry, yeah, absolutely, yeah, sorry, thank you. Okay, so that's the numerator, and then the denominator has some elementary factors, which is the square root of the discriminant raised to the power g. And then we have the torsion on the abelian variety, as well as the torsion on its dual. That's the general shape of it. For general abelian varieties. Now, I'm not going to say much about this. I just want to give you sort of a flavor of roughly what these conjectures look like, because I would like to specialize immediately to the case of elliptic curves over Q, or even modular abelian varieties over Q, where in fact, much more is known. In general, we know absolutely nothing of these conjectures, but for modular abelian varieties, we know at least one, and for two, we know a little bit as well. And so we'll see that coming back later on in this lecture course, when we study the work of Gross and Sagier and Kolibag. Okay. All right, so let's specialize to the case that we'll actually care a little bit more about, be a little bit more explicit about everything rather than just referring to the notes from many of these definitions. So we know 1. In the special case where A is actually an abelian variety defined over Q, and it's associated to some modular form F. So is modular, which is equivalent to saying that it's a quotient of the Jacobian of J0 of n, Jacobian of X0 of n. So modular, i.e., associated to some form F, which will be a cusp form of weight 2 and level gamma 0 of n, that is nu. Okay, so this F, for instance, it will have some Q expansion, and I'd like to fix the notation AN for its Q expansion coefficients. Now it's defined over, it's a new form, it's an eigenform for all the Hecke operators. It's defined over some finite extension of Q. In fact, we know quite a bit about this extension. It's totally real in general. So these coefficients AN have very nice integrality properties and algebraicity properties. Okay, now whatever they are, the L function LA, S, which has an a priori definition that you can find in the notes. You can also take the following as the definition, if you like. So it's the product of the L function of F sigma, which I'll tell you in a second what that is, where sigma runs over all of the embeddings KF, so this is going to be a power series where all the numbers live in KF, this finite extension of Q. And since it's a finite extension of Q, there's finitely many embeddings into the complex numbers. In fact, they're all real. So I told you this, you can take as its definition this product, and I have to tell you what the factors in that product are defined to be. Where L of F, S is simply the Dirichlet series of AN n to the S, where n is greater than or equal to 1. And if I put a sigma, I just let sigma act on these coefficients. I view them as complex numbers. Indeed, yeah. And so in fact, it'll be an elliptic curve precisely when the ANs are actual integers. So the degree of that field extension is the same as the dimension of the abelian variety, which is reflected in the fact that this is how many factors you get in this. Absolutely. Okay, so that's what the L function is. All right, so I claimed we actually know 1. And here's the argument for how that is proved. So we have, and this argument does 2 things. Well, it proves 1, and it also shows why on earth we would make this definition of the completed L function that we just made with these random looking factors that were completely unmotivated, but now they will fall out of this calculation. So it's very instructive to do this for yourself if you haven't done this already in some moment in the past. Okay. So I take this L function, LFS. The key is that this thing has a beautiful integral representation. And the integral representation is as follows. So this completed L function is equal to the integral from 0 to infinity of this function f, this complex analytic function in the upper half plane, evaluated at an argument it divided by the square root of n, okay, times t to the s, and then a dt over t. Okay, this equality I'll use, but it's an elementary calculation. In fact, it's the first exercise in the notes. Prove this equality. Very instructive. So you write down f as this power series, or sorry, as this power series here, where you remember that q is the exponential of evaluated 2 pi I tau. You plug this in, and then you do a variable transformation that essentially makes the sum come out and gets this independent factor, which turns out to be essentially a gamma factor up to that. It's a very nice exercise. So try and get this, this identity at least, which does one thing, it achieves a justification for this definition. Okay, so now what do we do with this integral representation? Once you've done this exercise, you can say, well, you see, this integral I can split up as the integral from 0 to 1 of this guy, it divided by the square root of n, t to the s dt over t, and the integral of the same thing from 1 to infinity. Not very deep mathematics. I'm sure everyone will agree with this equality, t over t. Now, why do I do this? Because you see, there's a very nice operator. It's called the Atkin-Lehner operator. I'll get back to this in a second. Wn, it's really a Fricke involution is a better name for it, because it's a specific Atkin-Lehner involution. So defined as the map coming from the matrix element -1 over the square root of n and the square root of n, and then 0, 0. This is a matrix element in SL2R. So you can make it act. In fact, it sits in the normalizer of the congruence subgroup gamma 0 of n. And that fact means that, so it acts on f by sending f of tau to f of -1 over n tau. So it's an involution in this way. It takes the argument tau, it switches it to -1 over n tau. And in fact, the nice thing about it is that it commutes with the Hecke algebra, and so therefore, so it acts on f, let me say it this way. As multiplication by a scalar. Now, f is an eigenvector for it, is what I'm trying to say. Now, since it's an involution, that scalar had better be plus or minus 1. And that's what I call small wn. So i.e., big Wn of f is the same as f multiplied by this scalar, little wn. Yeah, so either it's fixed by it or it's sent to minus itself. Okay. Now this is very useful because you see, what I've done here, this variable transformation here is made exactly so that these two domains of integration are interchanged by this Atkin-Lehner involution. So if I apply the variable transformation that I've written here on the board, I'm going to transfer this coordinate essentially to itself after a variable change, and the bounds of integration will switch from 0, 1 to 1, infinity. So again, this is exercise number 2. It's an easier one than this one. It's just showing that indeed what I say holds, and you get the following integral representation. The L function, where we have from this factor just a t to the s minus 1. That's just the second term. The first term transforms into this one after a change of variables, and it gives me minus wn t to the 1 minus s. It's a beautiful integral representation, which achieves many things all at the same time. First of all, it achieves the analytic continuation. Yeah? So you can see that now, when I've written this out, this is actually analytic in all s in C. And in fact, if I change the argument s to a 2 minus s, I'm exactly flipping these two exponents here. S minus 1 and 1 minus s are interchanged. And so in fact, we see that we get the same expression, but with this wn in it, or minus wn, which is this mysterious sign in the functional equation. So it's completely determined by the eigenvalue of the Atkin-Lehner involution, the Fricke involution. Okay, it achieves also a third thing, and that's something I profitably used in the notes. This is actually a very computable expression. So if I have a concrete modular form f, the values at s is equal to 1, for instance, and all of its derivatives can be computed by this expression. This is actually very rapid convergence. So if you have a computer, you can very easily now not just establish the analytic continuation, also compute the analytic continuation at points where you were previously not allowed to compute it using the naive definition. So it achieves many things at the same time, this integral representation. Maybe write a couple of words about that on the board. And if you look at the notes, they're completely riddled with examples, explicitly computed examples. And this one in particular is something I used many times in computing these examples. In fact, we'll do one together on the board in a second. Okay, so this gives three things. It gives the analytic continuation. It also gives the functional equation. And finally, it gives a very concrete computational tool. And if you're somewhat new to the Birchon-Swinnerton-Dyer conjecture, it's extremely instructive, and I put many examples in the notes, and I hope you'll do some of your own also, to look at what this prediction comes out to be in concrete examples. So pick your favorite elliptic curve over Q and compute everything. I just told you how to compute the L value and all of its derivatives using this formula. So you can at least compute this left-hand side, and then you can see what this term comes out to be and compute all of these terms, which will be a great opportunity to learn all of the definitions and see that the Birchon-Swinnerton-Dyer conjecture actually does seem to be true. Or not, right? In which case, maybe you disproved the Birchon-Swinnerton-Dyer conjecture, but that's pretty unlikely. Anyway, who knows, right? These kinds of computations are really fun. I'll just give you a summary of one of them, and since we won't really be talking about PSD that much and the nitty-gritty of all of these definitions, I'll be a little bit kind of brief about them, but the notes have all the details as well. All right, so they're really fun to do these kinds of examples. And so I just want to take one where I can point out a couple of things that I think are interesting to point out. So what we'll do is we'll do just a case of elliptic curves over Q, where everything becomes much more concrete. And in fact, I'll choose elliptic curves over Q that have conductor 11. Okay. Now, of conductor 11, there's precisely 3 elliptic curves defined over Q with that. You can look them up in Cremona's database for modular elliptic curves, and now we know all elliptic curves over Q are modular. So you know that this list is, in fact, complete. In fact, I can tell you what you'll find if you go to the LMFDB or other sources for this information. You find the following curve, which is y squared plus y equals x cubed minus x squared. That looks a little bit like the Diophantus curve that we started with n is equal to 1, except the x is an x squared. There's also an E2, which has the following beautiful equation, y squared plus y equals x cubed minus x squared minus 10x minus 20, also very nice. And then there's an E3, which probably I don't want to write down, but well, why not? X cubed minus x squared, and you see this one is quite a bit bigger. 7,820x. Please don't write this down, it's in the notes. So 263580. There you go. Now you have them. These are their equations. Okay? Everything is very explicit. Now it just so happens that all of these elliptic curves, conductor 11, are all isogynous to each other. In fact, there's 5 isogenies between them, interestingly. They happen to be all isogynous. In fact, looks a little bit like this. There's an E2, there's an E3, and then there's a pair of dual 5 isogenies between them. And then there's also E1, which is the one with the simplest Weierstrass equation, which also has these kinds of isogenies between them. Now, where do these come from? In fact, we can spot a couple of them already on the nose. So here, what we could do is we can make a little table also of the Mordell-Weil groups, computed by a 2 descent, but we'll do a little bit better later on, where I'll use a 5 descent on these curves to find their Mordell-Weil groups. Nonetheless, you can do it with a 2 descent as well. It's a bit of pain, or you just use an implementation of someone else, and you come to the conclusion that the Mordell-Weil groups are all finite, so you get a Z mod 5Z in both of these examples. Here, for instance, 0, 0 is a very nice point on it. It's of order 5, and that's in fact the whole torsion and in fact the whole Mordell-Weil group. The last one is trivial. So these are their Mordell-Weil groups. So they all rank 0, and they have different torsion groups a priori. Now, one thing that's kind of interesting is that if you quotient out this, you get E2, and then this one gives E3, etc. So you can go between them. But it's kind of interesting because you see, if we look at Burton, Swinert, and Dyer, it's a little bit funny. It's predicting that the L function knows about all of these invariants of these elliptic curves. But of course, the L function only depends on the modular form associated to it. So it's the same for all these 3 elliptic curves. So a priori, of course, all these arithmetic invariants could be different from each other. We see, for instance, the torsion up here, and the torsion already is different between them. So if Birch, Swinert, and Dyer is true, it had better be true that whatever this expression is, it's invariant under isogenies. So already it's quite fun to puzzle it out for these examples and to see exactly how you get a cancellation so that BSD is saved. Okay, so from here to here, we quotient out by a Z mod 5Z. That's the rational point 0, 0, the subgroup quotiented out by it. It takes you from E1 to E2. E2 also has a rational point of order 5, which I forget now what it is. Maybe someone knows. I didn't put it in my notes. Anyway, it's in the typed up notes. It also has a rational point of order 5 that you can spot. It's something easy, but I forget what it is now. It's like -1, 0 or something. Anyway, you'll spot it if you see it. That takes you from E2 to E3. Yeah? And of course, if these are all generated by an actual rational point, these 5 isogenies, the dual isogenies must have kernel isomorphic to mu5, because the Weil pairing exists, as we learned this morning. And so we get very nice isogenies going between them, and we understand also something about the Galois action on the kernels. Now, in the Birch, Swinert, and Dyer conjecture, there's a variety of different things to compute. The first is the real period, which for an elliptic curve is just, I look at the real points of this elliptic curve, so I draw my usual graph, my cubic, like we did with Diophantus in the beginning, and I integrate the differential form, the Tate differential form, so dx over 2y plus a1x, over the real component. So that's really just a real integral. You can write it down explicitly. I put it in the notes. Evaluate it numerically, and out comes some number. There is also the Tamagawa numbers. The Tamagawa numbers will look at all of the bad fibers, because at the good fibers, they're all trivial. And at the bad fibers, it'll look at how many components there are in the neuron model. So this is Tate's algorithm, as you can read about it in Silverman. And so here it happens to be, well, the only bad prime is 11, because the conductor is 11, and that's a prime. That these models look a little bit as follows. Yeah, so, and I'll focus specifically on E1 and E2. Over Z11, well, Z11 has 2 points. It has Q11 and F11. It's my base. And over that, over the generic point, I get my beautiful elliptic curve E1. And in the special fiber, it happens to be a nodal cubic with a singularity. Right? There's bad reduction there, but in fact, this is already regular. You don't have to blow it up anymore. Whereas E2 is a little bit less nice, and its special fiber looks initially like this as well, but it's no longer regular. You have to blow it up a number of times, and it gives you this special fiber. So it gives you 1, 2, 3, 4, 5. There's 5 components really in this special fiber. And so that means that the Tamagawa number is 5 in this case. It's a very concrete thing that you can check. And in fact, all of these invariants are also tabulated for you on LMFDB, even though it's much more fun to compute them yourself, as we do in the notes. Okay, so I make a little table here. So their BSD invariants are summarized in this table. Okay, so I'll make a little table where I have E1, E2, and E3, all of which associated to the same modular form, the unique cusp form of weight 2 and level 11. BSD predicts that the leading term of that L function is that complicated expression with all of these invariants appearing, so let's just compute. So there's the real period, which is an integral and a very computable integral, for which I found the following values, 6.3460, etc. It's an approximate value. E2 gives me 1.2692 ... And E3 finally gives me 0.2538 ... That's what these integrals turn out to be. Already there's something bizarre about these. I don't know if you see this, but if I multiply this one by 5, I seem to be getting this one. And if I multiply this one by 5, I seem to be getting this one. It's in fact true. You can prove that it's true exactly, and you can think about that for yourself if you like. Okay, so there is also C infinity, which is a number of real components when we draw the usual picture in the real plane, and it's connected, so it only has one. That's one fiber we have to check at infinity, and then the Tamagawa number at 11. I drew this picture for you, and so that shows me that for E1 it's 1, there's a unique component, and for this guy there's 5 components, yeah? And here also it's 1. I didn't draw it, but it's also true. Okay, so those are these first two terms. Then we get to the next term, which is the regulator. The regulator is the determinant of height pairings of generators for the Mordell-Weil group, but here they have rank 0, so the regulators are all 1. So they're not a very interesting quantity here to look at. The regulator of E over Q is just 1 in every case. Okay. All right, then we come to the problematic one. SHA. Well, we have no idea. We don't know we know something about its finiteness, and in fact, I'll get to that in the last lecture, but for now we have absolutely no idea whether this group is even finite. What we do know is, I told you this table, so implicit in that is that I already did a 2 descent on this. And after I've done this 2 descent, I will know that the 2 torsion in SHA, at least, is trivial. That's something, yeah? And so if the 2 torsion is trivial, maybe it's true that the whole group is trivial, but we don't really know, so I put a question mark behind it. Could be, we'll see. Finally, the only term left in this quotient, and if you look at the quotient that I've written there in horrible generality, we see a couple of things appear. Well, first of all, the square root of the discriminant, that's just 1 because we're over Q. And then we have the torsion on the abelian variety and its dual, but both of these are E. It's an elliptic curve, so it's the same as its dual. So we get the square of the size of the torsion. The size of the torsion is 5 in this case, it's 5 in this case as well, and it's 1 in this case. Now, does BSD look good? Does it look verified? Well, first of all, there's 2 things that we can check. The first thing we can check is if we make the BSD quotient of the leading term, at least it's the same for all 3 of these. And we see that we're saved here, right? Because the invariants jump all over the place. But there's an extra factor 5 precisely when we need it here, when we lost it here. And here we lost another one, so we needed 5 extra, and this one doesn't help us out anymore. But now this one does, because we're dividing by a 25 less than we used to. So okay, at least it's all the same for all of these curves. By the way, it was proved by Cassels that this expression is always invariant for isogenies, and then by Tate later on for general abelian varieties. What we don't know is what the L value is. I saved a little bit of space here. So they all share the same L function. Moreover, the value of that L function at 1 can be computed using this integral representation I've written down. I did this for you, and I got the following value. Numerically, we compute that the L value of any of these elliptic curves, so I'll just write LE at 1, it's non-zero, and in fact, it's approximately 0.2538. Independent computation, right? This didn't use any of the other invariants. Already, that looks like a familiar number. That's this number, at least to 4 digits of precision. So BSD looks right to 4 digits of precision. I secretly computed 20 or so, but it still looks right, trust me. So it's really fun, and I recommend doing this on a couple of examples for yourself, because you learn a tremendous amount about all these various invariants. We won't talk much about them. We'll just use BSD really as our motivation. So this is all kind of just motivational. But I still recommend you to work through a couple of these examples. It's really a lot of fun and it's very interesting to do. You can find a few more in the notes, including one also of an elliptic curve that doesn't have rank 0. So it's a little bit more interesting because the regulator term is non-vanishing. And maybe you can add some of your own for yourself. Okay, now, how do we attack this kind of conjecture? Yeah, so, yeah, absolutely. You could do it also by hand. That's quite interesting. So Gauss, for instance, has this algorithm, this AGM algorithm, that computes exactly these kinds of integrals super fast. You get very fast convergence. These are elliptic integrals. So people started studying elliptic curves precisely for this reason, to understand these integrals. But before they understood them theoretically, they learned how to compute them really, really efficiently. And then somehow throughout history, we forgot how to do the first one, and we understand much better their behavior. But it is something for which many algorithms are available. So strictly speaking, you don't need a computer at all. But if you have one, you might as well just make your life a little bit easier so you can do these more quickly. Yeah. All right. Now, what do we know about BSD? Well, you see, almost everything we know, in fact, I think it's fair to say everything we know about BSD comes from the modular parameterization that we learned about a little bit this morning. Because what is difficult about the BSD conjecture? It's about how do you produce as many rational points on an elliptic curve as possible? And I don't mean write down an equation for the elliptic curve and just try and find them by hand. I mean a systematic construction that works for any elliptic curve on a theoretical level. That's the difficulty in the BSD conjecture and in many conjectures in arithmetic geometry, producing algebraic cycles in some systematic way. And so virtually everything we know sorry? Yeah, or even the weak one, yeah. We know more about the weak one than we do about the strong one. So by strong, you mean the exact leading term expression. Yeah, exactly. So yeah, so this one we know much less about than the weak one. And in fact, I'll give you a number of results about the weak one later on. Yeah, so that was implicit in what I wrote here. So I wrote that the L function, unfortunately, I just erased it, but I wrote that the L function, let's do it just for an elliptic curve, should be S minus 1 to the rank of this elliptic curve over Q. And that's the leading term, yeah? So I also gave an expression, very explicit expression for what this leading term is, but already implicit in this is the fact that the algebraic rank and the analytic rank are the same. The analytic rank is defined to be the power that appears on this S minus 1 in the Taylor expansion. Yes, so this is the rank of EQ, when we write E of Q as a finite torsion group times Z of R. So this R is what I denoted by rank of EQ. Absolutely. The largest rank that known, I believe, is 28. This is what's that? By Noam Elkies, exactly. So he managed to construct an elliptic curve which has rank at least 28, but it has since been proven that if you assume GRH, it's actually exactly 28, and that's the largest rank that we know. Yeah, so indeed, yeah. So this is already quite old. We haven't found a larger one since then, and we don't know if there are any larger ones. So boundedness of ranks, that's a whole area that you can get into. There's lots of heuristics that predict how often you should expect to get a certain rank. Now, it's good that you asked, because it's maybe worth pointing out that in practice, if you take some random elliptic curve, you expect it to have rank 0 or 1 most of the time. In fact, 100% of the times if you set the counting up right. And within that, it should be 50% of the time should have rank 0 and 50% of the time it should have rank 1. In practice, we expect that most of the elliptic curves that we care about have rank at most 1. In later lectures, we'll actually prove things about elliptic curves of rank, or at least analytic rank at most 1. So that covers a lot of ground somehow. So it's good that you asked, because it shows. Yeah, indeed. So there's a theorem of Bhargava Shankar about the average ranks of elliptic curves, which I think is what you're talking about, which is good evidence towards that conjecture that I just told you, but it's a little bit weaker than what I just told you. The average comes out to be a little bit more than a half. I think it's like 5/6 or something, but I'm no expert on this topic. Yeah. Yeah. Yes. So right. So the fact that the rank, yeah. So the fact that the rank is finite was proved by Mordell, which is appeared 20 years after the paper of Poincaré. So Poincaré at most conjectured it. In fact, it's not even clear to me that he really explicitly conjectured it. It's somewhat implicit in what he writes. So we didn't know this until Mordell. Yes, Poincaré gives the name rank. But he doesn't say explicitly that it's finite. It could be infinite. All right, so virtually everything we know about the Birch-Swinnerton-Dyer conjecture and about those equalities comes from the systematic point constructions that are provided by cusps and mainly by CM points. Go about BSD. Comes from the modular parametrization, which we know exists for every elliptic curve E defined over Q from the modular curve x naught of n, where n is precisely the conductor of the elliptic curve E. Yeah? This is modularity. And so that's why now suddenly it becomes very interesting to construct systematically rational points on modular curves x naught of n. And while we're at it, we might as well do it for all modular curves of any type. And see whether we can understand any algebraic or rational points on them and how they map down to the elliptic curve. And that's exactly the strategy that has led to all the progress that we know. So we note, and this is just a teaser for what comes after, is this example that I picked, which everything today was motivational anyways, but this example that I picked was a little bit strategically chosen because E1 and E2 will be curves that are tremendously important for us in the next lecture. They're actually modular curves. So the previous example contains already an interesting test case. When n is equal to 11. Because it just so happens that x1 is isomorphic to that curve E1, whose Weierstrass equation I wrote down there, and x0 of 11 is isomorphic to E2. Yeah, so those two particular curves will come back a few times in what follows. One thing I didn't do for you today is I just claimed that their ranks were 0. I bluffed and I said I did the 2 descent. I actually did it, so that's not much of a bluff, but I just told you that the ranks were 0, sparing you all the pain and suffering that go into a complete 2 descent on this. They don't have any rational 2 points, right? So you have to go to a cubic extension, do all of the complicated computations, and out comes that the rank is 0. We'll prove it again next time or the time after that, but we'll prove it in a way that doesn't require any explicit equations. We'll do it using a 5 descent instead of a 2 descent. And that seems natural because these curves, they have 5 rational torsions. So why not use this 5 isogeny that's available for us? A good reason could be because 5 isogenies seems scary if you want to do a descent. How do I write down elements of the Weil-Chatelet group, etc.? Seems very complicated. Maybe we don't really want to do that if we're looking for just a quick answer. But the point is that using the ideas of Maser, and this will be our illustrative case for the general case that he does, you can actually do an explicit 5 descent on these 2 curves by pure thought. So you can arrive at the conclusion that the rank is exactly 0 without ever having to write down these explicit equations. And so next time we'll do that, and we'll ramp up towards the next case, which is n is equal to 13, and then I'll make some comments about how the proof goes in general. So this example, keep it in mind because it'll serve us well later on. With that said, I think I'll stop for today and I'll see you guys tomorrow.
Right. Any more comments or questions? If not, let's thank you again. And we restart at 4:30 with 3 shorter talks.